Okay, this presentation will give you a brief overview of some of the issues in modal analysis and Workbench and a few of the key steps in the process to help you out. Might be a good way to see an overview before you go through the analysis so you know what you're looking for, or to recap if you see something that's not working quite the way you expected it to. First of all, some key points on modal analysis. One is stresses can make a difference. So you can run with or without pre-stressing. In essence, pre-stressing many times will stiffen the matrix so that it responds differently than the unpre-stressed state, usually with higher frequencies. If you want to run pre-stress, first you need to run a static solution and connect the static structural results to the modal analysis. And the videos will show you how to do that, as well as the screen capture here in a minute. The other thing to understand is that sometimes you need to have nonlinear deflections on there to make sure that is handled adequately. As you'll see in the videos, that wasn't necessary in the examples that I ran, but it might be for your homework. The boundary conditions matter. So depending on whether, just think of a beam, is it a simply supported or fixed or cantilever? Those will have different frequencies. And so similarly, whatever you're modeling, you need to constrain it representative of reality. If there is rigid body motion allowed, your results will be irrelevant. You'll get essentially zero frequencies. The other thing to know is symmetry will eliminate some modal frequencies. If the mode shape is not symmetric with the geometry, then it will not be found by the solution if you just do a symmetric model. In terms of interpreting results, you want to look at the modal shape. The magnitudes you should not compare to. The shape is what you're looking at. So you probably want to plot the deformed body. And then look at your modal frequency. And then ask yourself, is this a frequency that's likely to be excited in operation? Those are the ones you have to worry about. And often, to first order, we're just trying to make sure that the modal frequencies are away from our operating frequencies or other forms of excitation. So in Workbench, there's a modal analysis solution, as you can see over here on the left. And so you're going to select that modal to run a modal analysis. And you can take that and drag that into the Workbench and use it directly as is if you don't want to do pre-stressing. So if you want to do a structural analysis as well, but don't need to pre-stress it, and you want to have the same mesh and the same materials, same geometry, then what you can do is you can first put in the static structural. And here I put a modal first, but I could drop a static structural over here. And then when I'm going to add the modal, I'll take the modal and I'll drag it over and I will drop it right on the model case as shown here on the left. If I want to do pre-stress effects, then I will take the modal and I'll drag it on top of solution, and that'll connect the solution over into the setup for that. So it'll include that initial pre-stress. Okay. So if I were to do both, so I have a static structural and I have this one, you can see it's connected to the model but not to the solution, then this modal up here would not include pre-stress effects. And this one is connected to solution, and so this one would include the pre-stress effects. You could also do that all with just this one by solving for a case where the stress is really low. This static structure up here could be used for looking at the static stress to see if it fail under static conditions. And when I open that up, and in that case where I have multiple things, each one of these is a folder there. So I will need, for static structure, I'll need to define my applied forces in the static structure. I will need to find supports in the static structure, as we've always done. In this modal analysis, where it says, notice how it says pre-stress none, that means it's not including the pre-stress. I will need to set my boundary conditions. So some displacements or supports that would keep it from moving and representative of the real situation. Down here in Modal 2, you see it's doing pre-stress from the static structural. So it'll inherit those boundary conditions, and I do not need to put in any boundary conditions in this state. Now, if you're going to apply a centrifugal force as a pre-stress, you'll find that under rotational velocity in the inertial tab, and that'll be displayed when you're on your static structural case. That will bring up this box here, and you need to determine the axis of rotation. This is in the component. You can also select vector, but this is under components, and then the center of rotation. In my case, I built the model around the 0, 0, 0 point, so that was good as is. You can also define your own coordinate system, and if you click on this, you can select a different coordinate system. When I'm looking at the modal analysis, since I'm interested in modal shapes, I may want to put in some deformation plots, and for each one of these plots, you can select which mode it'll show. And so I like to put in a separate plot for each mode, so it'll be 1, 2, 3, etc. on up to 6, or however many modes I want to set. And that number of modes is set under the analysis settings right here. Okay. And as I stated before, in the pre-stressing, often it's important to have large deflections on. So if at the least you should check and make sure whether that's dependent. And it will give you a warning if you run it without large deflections on, as you can see part of in the background there. So in this case, I've run the analysis, and I have a beam model, and I'm plotting one of the mode shapes. And there's a few things that you want to look at. One is the shape of the mode, so I can see that underneath all of these annotations. You can see it's fixed here, and it's kind of large amplitude there, and there appears to be a node around the midpoint run here. So that would be a shape. That would be one thing I'd be interested in. The other thing I'm looking at is frequency, and I can see that 3 places. One, it's on the edge of the plot. Okay. 2, when I have a plot highlighted, it's going to show all the modes that I solved for and their frequencies. And then graphically, those are illustrated down below. And finally, if I select my plot, here I have total deformation 2, and you notice down below there's this information. And if I expand that, frequency is an option, and I can make it a parameter so that I can see it in my parameters if I want to run a set of design cases all at once. Now, you'll notice here the displacement magnitude. This is, you notice the maximum it's listing is 76. Again, that's irrelevant to comparing these modes. You just want to look at the shape. Okay, so also I don't think it'll actually plot stresses, but again, those would be, the magnitude would be irrelevant if they did. Okay. So as we talked about, your case is to study when the vibrations are a problem. So you want to look at a point when the vibrations for frequencies at which the vibrations would be, the natural modes would be related, would overlap with the spinning speed of a CD. So you'll need to look up and see what the range of velocities of a speed or rotational velocities of a CD can be. There's a link provided on the assignment. And then compare that and solve for the modal frequencies as a function of the speed with the pre-stress, and see if there are points where those cross, and if and then tell us what that means for the likelihood of failure. Okay, so there's a good start. You can see the videos for some additional details as you walk through there, and feel free to reach out if you have any further questions.